when I was trying to decide what to talk about for this meeting, I thought that it would actually be a nice idea to kind of take a kind of significant piece of research that I've done in Lincoln and see if I could apply it to some old problems from the Korovka notebook, because I have a deep love of the Korovka notebook. When I was a new when I just graduated with my doctorate, I spent, I read the whole thing cover to cover looking for problems. So I went through and yeah, I found there's a problem from the 1980 edition, the 7th edition, by Alexei Fomin, where he asks for a description of primitive permutation groups, finite and infinite, that have a regular subdegree. And so this was about a week ago. I started kind of writing everything down and trying to turn it into a talk. But I realized actually that I think, I have something in the infinite case, but I think I can say a lot more. So yeah, so in the end, I decided not to talk about that because I think there's a lot more that can be said, particularly around where you have a wreath product action. So I'm going to work on it for a little more than a week, and but yeah, then it will be kind of gift wrapped, and I'll send it to you, Evgeny, and you can yeah, to celebrate 10 years of algebra here in Lincoln. So instead, I thought, as a local, I should kind of highlight a significant piece of research that's happened while here. And one of the things that I didn't really look at all before I moved to Lincoln was groups acting on trees for their own sake. I mean, they cropped up in my research, but really looking at them properly started to happen after I moved here. So I thought I would give the talk. This is like a slimmed down version of the plenary talk I gave at Group St. Andrews, the last Group St. Andrews, which yeah, highlights some of the work done in this lovely center of algebra research in Lincolnshire. So when I'm talking about all that work was with Colin Reid, who has been a very frequent visitor here in Lincoln. So some of his visits have been supported by the London Mathematical Society and my EPSRC standard grant. So we're very fortunate to be able to have him here, and he's coming again in well, very soon actually. Yes, so as a local, I think I should also, just reminisce slightly about why I moved here. I moved here because of Evgeny. I had a permanent position in New York, and I was very happy living in New York. My wife less so, and we'd visited Lincoln. It's a very beautiful city. And then one day we were sat in our very small studio apartment in Brooklyn, and Evgeny's email to the group pub forum where he said, "Oh, I'm starting a maths department in Lincoln," popped up, and my wife and I had visited. Well, she was my girlfriend at the time, but yeah, my wife and I had visited Lincoln when we were on holiday in the UK, and she was obsessed with it. She thought it was such a beautiful place. So I said, "Oh, this famous group theorist is starting a maths department in Lincoln." And then after that, she I think went on at me every single day that I should apply. So I started emailing Evgeny, and yeah, and then I said one thing that I did was I looked up sort of what was happening in Lincoln, and I saw this blog. I tried to capture the exact view that I had on that day in Brooklyn, and I remember thinking at the time, like, wow, Evgeny is a very, very busy man. All of these things popping up. So yes, now this lovely research community that Evgeny started continues to grow. We have recently appointed Yuri, who we're very happy is here. And yeah, so I don't know. I guess I hope that we can all meet like this again in 10 years' time for the 20-year celebration. That's in Lincoln. So what I'm going to talk to you about is groups acting on trees. There's a very famous theory for groups acting on trees, Basset theory. And what Colin and I have done is develop an alternate theory for groups acting on trees. It's dissimilar. It sort of fulfills a different role, but nevertheless, if you're familiar with Basset theory, the beautiful interplay between the kind of diagram that you draw based on the action, and then the action that you derive from the diagram and how they are all interlinked, is also present in our theory. It's a different diagram, it's different aims, but nevertheless, this sort of beautiful cyclical nature of the theory is present. So I hope to give you some sense of that. We also have it also, as a kind of like sign of its power, gives us a complete description of an important class of groups acting on trees, and I'll also talk about that. So it's the main point of the talk is about local actions of groups acting on trees. So throughout my talk, G is going to be an infinite group, T is going to be an infinite tree, and G is going to be a group of automorphisms of the tree. So what do I mean by a local action? Well, this idea of kind of local to global behavior of groups acting on trees sort of has grown into quite a topic now, but its genesis is sort of, or at least in its modern formulation, can be traced to Marc Berger and Shahar Moses' paper in 2000. Now, what do I mean by a local action here? So you've got a group acting on a tree. The local action at a vertex V, I mean, you look at the stabilizer of V in G, and then you look at the permutation group induced on the neighbors of V by that stabilizer. Now, a lot of the early work on this sort of it made assumptions about the trees being locally finite. In fact, a lot of the kind of interesting groups that you can get out of this come from when you relax that restriction, and so you don't place any restrictions on the cardinality of the set of neighbors of a vertex. So for that reason, we don't want to assume local finiteness. And then if you do that, we need to close the group in the permutation topology to define the local action. So it's not just the permutation group induced by the stabilizer on the neighbors anymore, it's the closure of that. Now, if you're not familiar with the permutation topology, I'll just say, yeah, you can think of two permutations as sort of being close if they agree on some large finite subset. And you can sort of picture what it might mean for a sequence of permutations to converge to another permutation. They agree on larger and larger finite subsets that will eventually cover the set being acted on. So the closure in the permutation topology would just mean throwing all of the limit permutations in as well. It's the standard thing in permutation groups to study the closed groups. Let's look at some little trivial examples. So if we look at T3, so when I write T with a subscript a number, I mean the regular tree with that valency. So this is the three-valent tree. Every vertex has precisely three neighbors. It's infinite. So the automorphism group of T3 well, what does the stabilizer of this vertex here induce on the neighbors? Well, it obviously induces S3, the full symmetric group. So you might then think, well, okay, what about, can I get a group with local action C3, cyclic group of order 3? Can I have something really nice and big, something close to the full automorphism group of that tree that acts locally like C3? And so let's kind of play around with this toy example. It highlights some of the issues that arise. So let's imagine we have such a group. Let's think about what it would look like, and specifically how close we can get to the full automorphism group. Well, it turns out that we can't get very close at all because our specified local actions sort of interact with each other and cause a collision. The stabilizer of V induces C3 and its neighbors. So if we look at the stabilizer of V and of W, we're fixing V now. We're also fixing a neighbor of V. Since we want it to be locally C3, that means we're going to have to fix all the neighbors of V. But we wanted it to be locally C3 everywhere, so that means it's locally C3 at W, but we're fixing a neighbor of W, so we also have to fix all the neighbors of W. Now we've got lots of new fixed vertices, and we're locally C3 at those, and we're also already fixing one of their neighbors, so we have to fix all their neighbors, and this kind of propagates out throughout the tree, and you end up fixing everything. So the stabilizer of the edge VW pointwise is trivial, and that means our group is discrete. So it's very, very far from being the full automorphism group. So the sort of moral from this little toy example is that, yeah, local choices for local behavior can severely restrict the global behavior of the group. Some conventions. So whenever I mention a graph, I'm going to mean in terms of Serre. So I can have loops and multiple edges. And unlike Serre, my loops may or may not be their own reverse. This is mainly for when we're drawing these kind of these diagrams we call local action diagrams. When I say trees, though, I also mean trees in the sense of Serre, but when Serre says trees, he means the same trees that everyone thinks of when they think of a tree. So no loops, no multiple edges, no cycles. And when I make topological statements, it'll be with respect to the permutation topology, which is also the topology of pointwise convergence. It's a very natural topology. So there's kind of three ingredients to what I'm going to be talking about. The first is sort of my reason for getting interested in groups acting on trees comes from the sort of perspective of permutation groups and the structure theory of locally compact groups. That's important because the natural tool you would seek to use there is Basset theory, and Basset theory doesn't work well in that situation. It has quite severe limitations. And so this local to global approach of Bergeron-Moses that now has its own kind of community around it really kind of broke through that. So I'll sort of give you the motivation from local compact groups. I'll talk a little about Basset theory. I'll introduce you to some kind of foundational local to global constructions. And then I'll talk about my work with Colin, where our aim was to sort of create an overarching theory that unifies these approaches. And then as a consequence, we end up with this very nice description of an important class of groups. Okay, so groups acting on infinite trees. The primary tool here is Basset theory. So I'll attempt to give a one-slide overview of Basset theory. I know there's some undergraduates in the audience as well, so I'll try and it's not going to have many details, but it'll hopefully give you an overview of it. Now, this overview, I'm going to frame it in a way that sort of highlights the need for an alternate theory, but also allows me to show the ways in which our alternate theory mirrors some of the beauty of Basset theory. So the idea behind Basset theory is that you have a group acting on a tree, right? And then what you do is you use that action to draw a little diagram. That diagram is called a graph of groups. And it's really just a colored graph. You draw a graph and then you paint the vertices and the edges. But you paint the palette that you're using to paint consists of groups, right? So every vertex is assigned a group, is painted with a group, and we call these the vertex groups. And yes, when you're talking about graphs in the sense of Serre, every edge you think of as a directed arc in each direction, right? One in each direction. So every arc is decorated with a group. And then there's the rule that the reverse arc has to be decorated with the same group, right? So you have to use the same color for an arc and its reverse. So we call that the edge group. And then you need kind of a monomorphism, just a way of seeing each of those edge groups in the corresponding vertex groups for the the two vertices that the edge is between. And when you do this, you have a graph of groups. And now the fundamental theorem of Basset theory, which I'll give for groups acting on trees without inversion, which means there's no element of the group that reverses an edge. This is the version that Serre gives in his book. It's a little cleaner than the general version. So since I've only got one slide, I'll give this version. The theorem comes in sort of two parts. The first part is that if you start with a group action on a tree, so you've got a group G acting on a tree T, then there's an associated graph of groups. So you draw the graph of groups. Now, that graph of groups, that little combinatorial widget that you've drawn, you can form its universal cover. You just walk around it and you have to pay some attention, but you then from that obtain a tree. There's also, in a similar sort of vein, but an algebraic vein, there's a group that you can produce from it called the fundamental group. So your graph of groups gives rise to a tree and a group, the fundamental group. And moreover, this fundamental group acts on the tree that is the universal cover of your graph of groups. So you started with a group acting on a tree, you drew a graph of groups, and from that you obtained a new group and a new tree, and a new action of this new group on the new tree. And it turns out that new action of a group on the new tree, it can be associated with your original action. So in some sense, this gives you a decomposition of your original action into the vertex groups and the edge groups, and then the graph of groups is sort of telling you how they embed in each other. So you can think of this side of it as being a decomposition. On the other hand, there's a constructive side, which is, let's imagine, as in fact I did when I was a naive doctoral student, imagine you want to build an example of a group. And you want it to act on a tree. Well, what you can do is you can just draw a graph of groups. You know then that the universal cover is a tree and the fundamental group is a group that acts on that tree, and you end up with an action on a tree. And Basset theory tells you that the stabilizer of that action will be, the stabilizers will be the vertex groups. The vertex stabilizers of that action will be the vertex groups, and the edge stabilizers will be the edge groups. Wonderful. Um, but there's a problem in that doesn't work if you actually want to retain control of the action, which if you're trying to build a specific group, you often wish to. So, okay, here's an example that we can all understand because of my toy example. Let's imagine I draw a graph of groups and I want my action on the tree, I want it to be locally C3. I want something that's almost the full automorphism group, but is locally C3. So I think of a group acting on a tree that has that stabilizer I want. So what would I pick? I'd pick, okay, I'll fix the vertex. This is in T3. I'll act like C3 on the immediate neighbors, and then modulo that action, I'll act like C2. So meaning that I can kind of, this is easy when I've got a board, but yeah, I do C3 on the first neighborhood, and then modulo that, I can interchange the 2 points coming off, and so on going out. So my group would look like C3, wreath, C2, wreath, C2, wreath, C2, wreath, C2, with this wreath product acting in its imprimitive action. Okay, I put that in as a vertex group. Maybe my graph of groups just has a single vertex and some loops. Well, we know ahead of time that that can't give me the action that I want on T3 because this group is too big to be a stabilizer that's locally C3. So we see here what the problem is with Basset theory. When you're using the construction side, you have to you lose complete control of the action of the permutational behavior, and that it turns out to be a big problem when you're working with locally compact groups, right? Because we're really hunting for examples often, right? So the decomposition works well, but the construction side, we have problems. Let me just mention briefly why we might be interested in such things, right? So, the general structure theory of locally compact groups starts with a decomposition into the connected and the totally disconnected cases, and I guess there's an extension problem that no one ever talks about. Now, the totally disconnected case is usually abbreviated to TDLC, and the connected locally compact case is a different beast. Following the solution to Hilbert's fifth problem, we know the broad structure of connected locally compact groups. We know they're pro-Lie groups, so inverse limits of Lie groups. And so there's been a huge amount of focus then now on the totally disconnected locally compact case. And in particular, on the compactly generated case. The reason for this is, compact is the sort of topological version of finite, and the compactly generated groups, the compactly generated TDLC groups, have lots of nice structure, right? So they have a geometry that arises from a locally finite graph called the Cayley-Arbels graph. So there's an interplay between the geometry and the topology that you can use to say very nice things. So the same reason that people like finitely generated groups is the same reason that people focus on compactly generated TDLC groups. Now, there's a very beautiful result by Pierre-Manuel Capras and Nicolas Monod that says that the structure theory of compactly generated locally compact groups depends on this class script S. Sometimes script S is restricted to the totally disconnected case as well. So you have to be a little careful of that if you're reading stuff. But S is the class of these compactly generated, locally compact groups that are non-trivial and simple. So I mean non-trivial from the point of view of the theory of topological groups, so that means non-discrete, and simple from the point of view of this theory, so that means topologically simple, no closed, non-trivial, proper normal subgroups. So that's what the class S is. And the main source of nonlinear examples from S come from groups acting on trees. So hence the interest in them, right? And the very first example came from Jacques Tietz, right? So he was answering a question of Jean-Pierre Serre, where Serre was looking for nonlinear, abstractly simple, compactly generated locally compact groups. And says, I mean, Tietz's example comes from groups acting on trees. So it relies on this notion of independence, which we now call Tietz's independence property P. And yeah, it's sort of easy to picture what this independence property is. So you imagine we've got a group acting on a tree. I'll again use T3 here. So what we're going to do is we're going to have to quantify over all finite and infinite paths. So you start with a single path, let's call it Q, in your tree, and you pointwise stabilize it. And then you look at the subtrees hanging off this fixed path, and you ask whether the pointwise stabilizer of this path acts independently on these subtrees. So what do I mean by that? I mean, if my pointwise stabilizer of Q induces some automorphism on this yellow subtree, can I still induce the same automorphism of that yellow subtree if I fix pointwise everything in the tree that isn't in the yellow subtree? So when that happens, your pointwise stabilizer of the path decomposes as a direct product, and you can kind of do whatever you like on each of the dangly bits. So if we can do that for Q, then we might say that we have independence around Q, and then we just test it for all the paths. If we have independence for all the paths, then we say that, that the group has Tietz's independence property P. There's an obvious, you don't immediately get a simple group. There's an obvious normal subgroup sitting inside a group acting on a tree, arising from the group generated by pointwise stabilizers of edges. So we call that, if G is our group, we call that G plus. And then Tietz's theorem says that if you've got a group acting on an infinite tree that has this independence property P, then as long as the group doesn't do something that obviously jeopardizes the simplicity of G plus, so that is, it doesn't leave invariant some non-empty proper subtree, and it doesn't fix an end, as long as it doesn't do those two things, then G plus will be abstractly simple. So now you can answer Serre's question by just looking at T n plus. So remember, T subscript n is the n-valent tree. Every vertex has n neighbors. The automorphism group of that, and then we simply look at the group generated by edge stabilizers there. That was obviously nonlinear, and it's compactly generated, locally compact, and abstractly simple. And obviously obviously non-discrete in this case. So it was a sort of an important question in the area of locally compact groups. Sort of how large was this class S? How many isomorphism classes were there in S? And so one way that you might think about tackling that is to generate lots of examples, and a sort of naive way would be use Basset theory to build large, by which I mean non-discrete subgroups of Tn, make sure they have property P, and then apply Tietze's theorem. And yeah, as we've seen, that's difficult, because if you want to argue that you're still within Tn, and you also want to argue that you're kind of somehow close to the size of the full automorphism group, you really need to know that you haven't lost control of your permutation representation. And yeah, and as we've seen, you can't do that using Basset theory. So the sort of first step in an important milestone in this was the kind of local to global universal group construction due to Marc Berger and Shahar Moses. Now, those of you that are familiar with Basset theory will know that the sort of fundamental or foundational, I should say, roles played by the H&N extension and the amalgamated free products. Now, in our theory, the kind of foundational examples are the Berger-Moses universal group and a group that's due to me called the box product. And they kind of play, well, I'll right at the end, I'll kind of point out the similarities between these. So what I'll try and do is introduce these two constructions at the same time, the Berger-Moses group and the box product group. The ingredients into these groups are permutation groups. So let's imagine that we have now two permutation groups, M and N, and all this works without the transitivity assumption, but there's a little more, there's just, the statements are less clean, so I'm going to say it all for transitive groups. So M acts on a set of cardinality little m, and N acts on a set of cardinality little n, but there's no restrictions on those cardinalities. We've already seen what it means to be locally M. When I say something's locally M, I mean it just has local action M at every vertex. So, you know, in T3, like if the group, when it fixes the blue vertex, induces C3 on the neighbors, we would say that's locally C3. So we've already seen that locally C3 groups are very restricted in T3. There's another type of tree that's like the regular tree called the biregular tree, where every vertex has valence has either m neighbors or n neighbors, and it alternates, right? So one part of the bipartition has valency m, and the other has valency n. And so I've kind of highlighted these two bipartitions in blue and red. And if you're locally Mn, it simply means that you, when you pointwise stabilize a vertex in one part of the bipartition, you induce M on the neighbors. And when you pointwise stabilize, when you stabilize a vertex in the other part of the bipartition, you induce N on the neighbors. Or to be, yeah, that's fine. So here, you know, this would be like a locally C3D4 group if this played out across all the vertices. Okay, so let me introduce the groups. I'm not going to construct them because I don't have time, but I can at least tell you their important properties. So the Berger-Moses group, UMN, is a subgroup of the automorphism group of the M regular tree, we denote it by UM, that has some nice properties. And the box product group UMN is a subgroup of the automorphism group of the biregular tree, TMN, that also has similar properties. The first properties that are striking is they both have Tietze's independence property P. So immediately you start thinking, these could give me simple groups in S. They both also enjoy the universal property. So the universal property for UM is that every there's a copy, a permutationally isomorphic copy of every locally M subgroup of ORT M sitting inside U of M. And the universal property for UMN is that there's a permutationally isomorphic copy of every locally MN group of subgroup of ORT TMN sitting inside UMN. U of M has a simple subgroup of index 2, and UMN is itself simple whenever M and N are generated by point stabilizers. So, for example, if they're primitive permutation groups, non-cyclic primitive permutation groups, then you end up with a simple group. So I think it's fair to say that the majority of new constructions of groups in S have used the ideas of Shagtid's and property P and its generalizations, or the ideas of Bajor and Moses. And this second construction, the box product construction, I used to answer the question of how many isomorphism classes there are in S, by showing there's 2 3 if null of them, and moreover, classifying this class up to isomorphism is at least as hard as classifying the 2 generated groups up to isomorphism. So they're really these groups acting on trees really are playing a fundamental role in the theory of locally compact groups. Okay, so what about the theory of local action diagrams? So a local action diagram, it's slightly more complicated than a graph of groups because it's encoding more information, but it's a group, some colors, and some groups. Sorry, it's a graph, some colors, and some groups. Right. So the graph is just a connected graph. So here I've got a graph, 2 vertices, 2 edges. I'm splitting the edges into arcs. For each arc, we have a set of colors. So here I've drawn on like it has 3 colors. The reverse of, B has 2 colors. The reverse of A, I've given it infinitely many colors, and I've given it a kind of unusual color set, just to illustrate that it can be anything. And then every vertex is assigned a group, which we call the local action. And the local action has the following properties. It's a group of permutations of the colors of the out arcs from that vertex. So just to kind of highlight it here, so the local action at V is a permutation group on these colors. And as I'll reveal in a second, the orbit decomposition of that action corresponds to the breakdown of those arc colors into the arcs they correspond to. Right, so this local action has 2 orbits, this and this local action has 2 orbits, this and this. And yeah, we also need it to be closed. And as I mentioned, the arc colors codify the decomposition into orbits. And that's it. There's nothing else to it. So you can easily doodle lots of these things if you wish. There's a natural notion of isomorphism, which is just a graph isomorphism with permutational isomorphisms of the local actions. If you spent 5 minutes, this is probably what you would come up with. Now, if you're given a group acting on a tree, then there's an associated local action diagram. So this is behaving like a graph of groups. We also have a converse, that if you draw a local action diagram, then it gives rise to a special arc-colored tree. So this is kind of analogous to the universal cover of a graph of groups. We call this a delta tree. It also gives rise to a group, which we call the universal group, which is playing the same role as the fundamental group, although it's fundamentally very different. It's sort of in spirit very well. It's a generalization of the Bajor-Moses group and the box product group. And moreover, this universal group acts on the delta tree. So what do you get out of this with some work? The first is that the universal group of a local action diagram is closed and it has Tietze's independence property P. So for brevity, we call this P closed. And of course, then you can think of the P closure of a group as being the sort of smallest supergroup that's got property P and being closed. And so I denote that by the P closure of G is G to the power P in brackets. The universal group of a local action diagram has a universal property in that if you've ever got a group acting on a tree that has the same local action diagram up to isomorphism, then there is an permutationally isomorphic copy of that group inside your universal group. And moreover, there you have equality precisely when G is P closed, when it's closed with property P. So that then allows us to prove a structure theory that's quite striking. The first mirrors the decomposition result for Basset theory, that you've got a group acting on a tree, then you can form the local action diagram. That gives rise to a new group and a new tree. This new group acts on the new tree in such a way that it can be associated with the original action of the P closure of the group. So you lose a small amount of information there. Basset theory, you recover the original action. Here we recover the action of the P closure. But that sacrifice gives us, on the other side, on the construction side, that if you draw a local action diagram, and of course they're nice and easy to draw, there's not much to check, then you obtain a tree and an action. But moreover, you have complete control over that permutation group. You know exactly what it is, you know exactly what it does, and it's P closed. So this then allows us to kind of just manufacture, lots of these simple groups kind of willy-nilly. And then as a really nice sort of icing on the cake, it turns out then that this very important class of groups, these groups with Tietze's independence property P, we end up with a complete description of every closed group with property P. So that means that we end up with a complete classification of every group with property P. We know what every P-closed group looks like. They are precisely the universal groups of local action diagrams. So some remarks. Let me give you some examples. The Berger-Moses group is just the universal group of a local action diagram consisting of a single vertex with some loops that are its own reverse. So if you're familiar with Basset theory, that might make you think of the graph of groups of an H&N extension. The box product group is the universal group of a local action diagram consisting of two vertices connected by an edge and no loops, which, again, Basset theory, the amalgamated free product graph of groups has a similar sort of combinatorial structure. Something that's very, that might not have struck you is that because we know that every closed group with property P arises the universal group of a local action diagram, that means all properties of that group are encoded in the local action diagram. So that means that you can read all the properties of this group directly from the local action diagram. So for example, if you want to look for, invariant subtrees that are proper and non-empty and fixed ends, and you want to make sure there aren't any, that's you can tell that immediately from the local action diagram. These arise from what we call strongly confluent partial orientations. But that means then that you can, if you're given a group acting on a tree with property P, you draw its local action diagram, that tells you that you can read off from the local action diagram whether the group is simple. So long as it satisfies the property, there's no, as we call them, scopos, strongly confluent partial orientations. So it's very, very powerful. There's also lots of obviously lots of questions arising from this. We've got a huge number of questions in our paper. Some of the, if you're interested, do write to Colin, right? Because there's various groups around the world that are working on some of them. But yeah, there's lots of nice questions, both in the original paper and we've written a kind of a friendly survey paper as well that should appear this year. So yeah, thank you very much.